Hello everyone, my name is Mariia Bakhtina and today I will present the work which we have done at the University of Tartu. The title of this talk is Information Security Analysis in the Passenger Autonomous Vehicle Interaction. With the push of innovation, automotive industry moves towards automation. And autonomous vehicle, or just AV, is defined as a system that is able to conduct dynamic driving tasks with limited human intervention. And once the technology reaches fully automation level, there will be no need in a driver, and AVs will be used to enable our easy transportation. But passengers still should be engaged in some sort of dialogue with the AV. And such a dialogue is called passenger-AV interaction, and it enables passenger to get information about AV behavior and to conduct supervisory control over it. But such interaction should be supported through some central system which helps to initially establish the interaction, and passenger can also use electronic devices to support this interaction. Meanwhile, the proof-of-concept attacks highlight the lack of AV information system protection, and unfortunately, currently, there is no on-the-shelf solution of information security in the AV. That is why our works aim to define how can information in the passenger-AV interaction be managed. This presentation is structured as follows. We started from giving short motivation of the research and will continue with the related works. Then we will look in the case scenario which we used and the used research method. Then we will proceed looking at the security risk analysis which we conducted for the case scenario, and finally we will finish with the concluding remarks. So far, numerous studies have attempted to address information security and corresponding risks in autonomous vehicle and connected autonomous vehicle, looking at this problem from different perspectives. However, most of these researches are focused either on security of in-vehicle components or vehicle-to-infrastructure and vehicle-to-vehicle communication, while AV-human interaction is mostly considered as the interaction with the pedestrians. And additionally, there exist several comprehensive guidelines, for example, from European Union Agency for Cybersecurity, ENISA, and Information Technology Promotion Agency in Japan, IPA, which give high-level recommendation on the security efforts in the phases of automotive system lifecycle. However, they are not scenario-oriented, but rather focused on the functionality of the systems. And this paper is complementary to the earlier works, aiming to illustrate the first stages of information risk management by incorporating more detailed attack methods discovery for managing risks and this on the scenario level. The research was conducted in the form of case analysis, and to capture the passenger-AV interaction scenario, we used the user interface prototype, which was designed for the ride-hailing company in the autonomous driving lab. For the case analysis, we used the business process model, which depicts this interaction. Generally, passenger-AV interaction is a part of ride fulfillment process, which consists of three main steps. It starts when passenger initiates the ride, for example, using mobile app. Then ride execution takes place when in-vehicle control this part, and it is finished with the required post-processing of storages and algorithms for improving further user experience. And as only the second part of this process contains direct interaction of passenger and AV, we will focus only on it. For presenting the interaction, we created the business process model using the BPMN language. So once the vehicle reaches the starting point, it notifies the central system, which notifies passenger about it on the mobile app. Then passenger can enter the ride, authenticate himself, and initiate the ride. Then, during the move, AV conducts dynamic driving tasks and shows the ride state to the passenger, while passenger can manage the ride by changing driving style or the destination. And finally, approaching the destination, passenger can select the spot to get off and is asked to leave the car. As we can see, this interaction embraces several systems which communicate with one another. Secondly, there are data flows of different nature. Either it is the data taken from the storage, or it is generated during the ride, or it is captured from the passenger. And thirdly, the loss of information security within this process may impact passengers' privacy, safety on the road, and lead to the financial losses. And that is why it is vital to conduct security risk management in order to mitigate all these risks and to increase in general social trust in the autonomous vehicle technology. In this work, we use the threat-driven approach of security risk management. And additionally, as the baseline, we used the ISSRM domain model, which orchestrates security standards by covering 3 concept groups important for information security assurance: assets, risks, and risk treatment related concepts. The research method was the following. Firstly, based on the attacks and threat libraries and taxonomies, we developed a theoretical threat model for the interaction scenario. Then, using security countermeasures libraries, we elicited abstract security requirements which aims to address these threats. And then we applied these theoretically developed artifacts to the concrete scenario. And to do so, firstly, we defined what are the assets that requires protection, considering the system architecture and data structure. Then we applied threat model to these assets, defining what are the security risks. And finally, we instantiated abstract security requirements in the context of the research system to define how these risks can be reduced. So the main result of our work is the developed threat model, which was proposed to use as the baseline for elicitation of security requirements for the AV system in the passenger-AV interaction. So let's look at the model development. As an input, we used threat and attacks taxonomies and libraries, namely KPEG, ATT&CK, OWASP, and additionally STRIDE approach. So we revised these libraries to pick those attacks that are relevant for the passenger-AV interaction. And this resulted in the presented on the slide 17 threats, which are aiming to harm the business assets by exploiting system components vulnerabilities. And threats in the model are grouped by the primarily caused harm and the attacked vector from the STRIDE approach. It's also worth to mention that the threats in the model are interconnected because implementation of one of them, for example, session hijacking, may enable implementation of others, for example, identity spoofing and so on. And the threat model is also supported with the detailed description of each threat components, highlighting the source, targeted vulnerabilities, attack method, and prerequisite for the threat agent, and additionally the possible caused harm. On the next step, we aim to elicit abstract security requirements, so we revised such libraries of security controls as SIS version 7.1 and special publication of NIST, and conducted another round of threats and attacks libraries review, which resulted in the elicited 56 abstract security requirements, which are based on the best practices of prevention, detection, and correction of the threats. And thereby we finished the development of theoretical artifacts, and now let's look at how they can be used. Here we are looking at the defined model of assets in the form of class diagram. So knowing what are the business assets, which security criteria for them should be ensured, such as confidentiality, integrity, and availability, and defining which system assets support these business ones, we can move on to the next step. So let's look at how this threat model can be applied to the business assets. From the previous step, we know that there is an asset called passenger notification, which is used to inform passenger about current location. And there is the risk that an attacker will implement one of the information disclosure threats, namely man-in-the-middle attack, placing himself in the transmission channel between the autonomous vehicle and the passenger. So he will sniff the information exchanged between the process participants and eventually will find out the passenger's location during the ride. And in order to manage this risk, service providers should consider implementation of such requirements as identifying unauthorized connections to the local area network, ensuring confidentiality of the transmitted data, for example, using secure protocols, and controlling physical access to the transmission channel within the facility, so the AV. The application of the threat model in the context of assets in overall resulted in 22 security risks, which either directly or indirectly may impact security criteria of the assets. And the mitigation of risks were defined in the form of security requirements, instantiating them from elicited earlier abstract ones, which are mostly system requirements, but the full set also consists general requirements for the service provider. And in overall, it resulted in the elicited 64 requirements, which are aiming to address the defined security risks. To sum up, we looked at the application of the threat model-driven approach for security requirements elicitation, which is based on the developed threat model for the passenger-AV interaction. The main limitation of the work is the scope, which is limited by exactly passenger-AV interaction and mainly focused on the application layer of the AV system. However, for ensuring information security on the driving autonomous vehicle, information security risks should be also managed in the other processes within the AV and in the scenarios of other communication. And in the future, the further validation of the proposed approach is needed to done, and additionally, conducting the similar research for other interaction scenarios will, for example, the cases when few autonomous vehicles communicate during the ride or when few passengers participate in the ride can be conducted, and this will enable further validation of the approach and also generalization of information security risk management in the autonomous vehicles. And this concludes my presentation. Thank you for your attention.